Welcome to Organic Chemistry 101, and in this series we will discuss about different organic chemistry topics stepwise. So we start with reactive intermediate, which is a very important organic chemistry topic. Now, what is a reactive intermediate? In organic chemistry we study reactions, right? So whenever a reaction occurs, if you have a starting material here which I represent by R, so it will go through one or more than one steps, and that will lead you to this product P. Now in between there can be several species which can be formed in the reaction, and these are called intermediates. So intermediates are the species which are formed in between reactions. In some cases you can separate the intermediate from the reaction mixture, but mostly they cannot be separated because they are highly unstable species, they are high in energy. So what are the most common intermediates? They are carbocation, carbanon, free radical, carbene, benzene and nitrene. These are the common intermediates. Now in this lecture we will discuss about carbocation. So carbocation, as the name suggests, it is the species where positive charge is on the carbon atom. So we will discuss about generation, stability and reactions of carbocation in this particular lecture. First, let us talk about generation of carbocation. Now I am representing these two reactions, this one and this one, how carbocations are generated. So in the first reaction you can see you have this unsaturated compound, the alkene, where if you do protonation with acid you will get this carbocation. So in one side of this double bond, so here you have this proton, and in one side of the double bond the protonation occurs, and as a result you get this carbocation. So this is how carbocations can be generated. Another way of generation of carbocation is by the removal of some leaving group. In this case bromide is leaving as the leaving group, so bromide you are getting as leaving group and you are getting this carbocation. Similarly, if you have tertiary alcohol, and if you do protonation of that, you can also generate carbocation because water will be eliminated and you will get this carbocation. So this is how you can generate carbocation, either protonation of some unsaturated species or by the removal of some leaving group like halide or water, etc. Now let us talk about shape of the carbocation. So what do you think, what will be the correct shape of a carbocation? Now we can have two shapes, either one is this one where you have this pyramidal shape. This is the pyramidal shape, similarly like ammonia. If you recall the shape of ammonia, the difference is in ammonia you have lone pair, and in this case you have vacant p orbital. This is the vacant p orbital. Another possibility is this planar shape. Now what is the difference between these two? Let us see. So in case of pyramidal shaped carbocation, you can see the positive charge is closer to the nucleus. Why I am saying that? Because you are placing the positive charge on the sp3 hybridized carbon atom, and because the carbon atom is having more s character in the vacant orbital, that means it is not a stabilizing situation. And also you have these groups, the angle between these groups are close to 109 degree. Okay, so they are close to one another, so there will be repulsion, there will be a steric repulsion. Whereas in case of this planar carbocation, you can see the positive charge is placed on p orbital and not sp3 hybrid, so it is away from the nucleus. And also you can see the angle between all these groups, it is 120 degree, which is much bigger compared to 109 degree in case of pyramidal shape. So that means there is less steric repulsion among all these groups. So that's why normally carbocations prefer planar shape. There is another reason to this which we will discuss in the next slide. So now let us talk about So this is not the actual shape, the pyramidal shape, but actual shape would be the planar shape. Now let us talk about the stability of carbocation. Okay, so stability of carbocation depends on three important factors. One is inductive effect, next one is the conjugation, and the third one is the hyperconjugation. These three factors stabilize a carbocation. In this example you can see all the factors are present except the conjugation, because this is the carbocation center, positive center, and all these methyl groups, they are pushing electrons by the inductive effect. So inductive effect is present there. Also you can see this CH bond is there, this CH bond, so it is participating in hyperconjugation with the empty p orbital. So it is also called sigma donation. So either you can call it sigma donation or hyperconjugation, but it is stabilizing the carbocation. Similarly in this case also you can see this sigma donation is there, and here also this sigma donation is there. So whenever sigma donation or hyperconjugation is there, the carbocation will be stable. In this case you can see conjugation is there, so this double bond is conjugating with this carbocationic center, so that's why it is stabilizing. Another example is this one. You can see this is the order of stability of different carbocations. In this case it is methyl cation, and there is no inductive effect, no conjugation, no hyperconjugation, so this is very much unstable. When you put one methyl group, the stability increases. When you put two methyl group, stability increases further, and the three methyl group, that is the tertiary case, the tertiary carbocation is the most stable among all these three, because here you have inductive effect and the hyperconjugation or the sigma donation. So this is how carbocations gets stabilized. And you can see in the planar form only this p orbital can do a proper overlap with the sp3 hybrid. You can see this sp3 hybrid and this p orbital, the overlap will be maximum in the planar state. That is another reason why planarity is there in the carbocation. Okay, so you can say that to gain the stability through hyperconjugation, carbocation go into the planar state, or you can say that because it is in the planar state, the stability is there. Either way you can explain it. Now let us see some examples of stable carbocations. So you can see these are some examples of stable carbocations. In this case you can see this is the tertiary carbocation and this is the secondary carbocation. So of course the tertiary will be more stable because there are more inductive effect and more hyperconjugation, so that's why it is a good substrate for SN1 reaction, because in case of SN1 reaction the generation of the carbocation is the rate determining step. Similarly this is allylic carbocation and this is benzylic carbocation, both are stabilized by conjugation. So here conjugation is there, in this case conjugation is there, so in both cases conjugation is there, and that's why they are stabilized carbocation. Similarly you can see heteroatom, oxygen or nitrogen, they can also stabilize carbocation by conjugation. So this oxygen lone pair can donate, or this nitrogen lone pair it can donate to stabilize the carbocation. And of course in case of nitrogen the donation will be much stronger because nitrogen is less electronegative than oxygen, so this carbocation will be stabler compared to this one. Okay, so this is how you can explain the stability. Let us see some more examples of stable carbocations. So you can see we have a list of different species, and we are comparing the rates of solvolysis reaction, basically SN1 reaction. So the rate will be directly proportional to the stability of the carbocation, because more easily the carbocation is formed, the reaction will be more faster. Okay, so now if you compare all these things, you can see, so we arbitrarily put these as rate of 1. Okay, this allylic chloride rate as 1, so this chlorine goes and you get this carbocation, this allylic carbocation from here. Now if you compare this with all other, you can see for this the rate is 0.07. all these are arbitrary scale. Okay, so this is 0.07, so that is implying it is much lower rate compared to this one, and it is also implying that this carbocation here, this carbocation is relatively less stable, much less stable compared to this one. And we can explain it because there is no conjugation, there is only inductive effect and some hyperconjugation. Similarly for this one, the degree of inductive effect and hyperconjugation increases, but still there is no conjugation, and that's why the rate is more compared to the first one, but it is lower than this one. But when we go to this tertiary center, you can see the rate is much higher compared to this one. Now because in this case you are getting this tertiary carbocation, which is much more stable, because here you have inductive effect from 9 hydrogen atoms and inductive effect from 3 methyl groups and hyperconjugation from 9 hydrogen atoms. So tertiary carbocation is much more stable. Now this is another allylic case, but in this case you have extra methyl group, so stability is increasing compared to this one and rate is higher. In this case you can see it is also allylic and you are putting 2 methyl groups, so stability of carbocation increases much more and you are getting a tremendous 13,000 fold, 1,30,000 fold increase in the reaction rate. In this case you can see this is benzylic case, like benzylic, not exactly benzylic, because it is allylic and this phenyl group is at the terminal, so this phenyl ring also in conjugation with this, and that's why the stability is higher, but it is lower than this one. So we can say that the effect of alkyl group in stabilizing a carbocation is much higher. Okay, so we can say that. Now let us see some unstable carbocation. So most unstable carbocation would be this one, this methyl carbocation, because you don't have any inductive effect, hyperconjugation or any type of conjugation. So generally you cannot generate methyl cation, it is quite unstable, very much unstable. Another one is this one, you can see this is a carbocation on the bridgehead. So this is also impossible, because in the bridgehead position, the position is such that it is rigid and this orbital, this particular orbital is in such a position that it cannot undergo overlap with any of the sp3 hybridized CH bond. So there no hyperconjugation is possible there, and planarity, which is one of the criteria for the carbocation for its stability, cannot be achieved in this case. So because planarity cannot be achieved, it is very much unstable and you cannot generate this bridgehead carbocation. Okay, so these two are classic examples of unstable carbocations. Now let us look into the reactions of carbocations. Okay, so carbocations, they are electron deficient species, so they readily undergo reactions with nucleophile. So one of their reaction is reaction with nucleophile, another is they can eliminate a proton, that is basically elimination reaction, and the third category of reaction is rearrangement reaction. So let us see some nucleophilic reactions. So you can see these are some carbocations. So this carbocation and this carbocation, they undergo reaction by this nucleophile, in this case chloride and in this case iodide. Okay, and you get this chloride species and iodide species. So basically these are examples of addition reaction. In the first step you generate the carbocation and then you add the nucleophile. So basically this is addition of the HX across this double bond. So these two are examples of addition reactions. This is another example of addition reaction where sulfur is added, SH group is added. So these three are addition reactions. Okay, and this is the example of substitution reaction. In the first step you generate the carbocation by removing the water. You can see this carbocation is generated and then bromide is attacking on this carbocation to give you this bromide species. So this is nucleophilic substitution, SN1 reaction. So both are addition of nucleophile on the carbocationic center. So this is one category of reaction by carbocation. The next category of reaction is this one. So in this case you can see elimination. So basically in the first step carbocation is formed by the removal of water, and now the proton is eliminated by some weak base, in this case this sulfate. This sulfate is eliminating the proton and you are getting this alkene species. So this is elimination reaction. So this is another reaction of carbocation. The next reaction is the rearrangement reaction, and this is interesting. You can see in case of rearrangement reaction, this is the species which is rearranging to this, you can see. So how it is happening? So in this case you can see in the first step this silver plus Ag plus, it is forming a complex with this iodine, because see iodine has affinity towards the silver. So it is forming this complex, and now it becomes a beta leaving group. So iodide goes and it goes as a leaving group. So in expelling this iodide, this methyl group and this CH sigma bond, this assist. Okay, you can see this is the assistance. Okay, and this assistance it forms this transition state. Okay, so this is the bridging carbocation. Now by doing that, it migrate from here to here, it migrate from here to give you this, you can see. And by this migration, you are generating this more stable tertiary carbocation. So if you skip this one, you can represent the same reaction in another way also. So you first generate this primary carbocation, which is very much unstable, and then you migrate this methyl group onto this primary center, so you get this. Okay, and now the water molecule attacks on this tertiary center, and you get this alcohol. So this is how the rearrangement occurs. Another example of rearrangement would be this. So in this case, you can see this is chloride, and in the first step you eliminate this chlorine to form this secondary carbocation. Now this secondary carbocation rearrange itself towards this tertiary carbocation, which is much more stable. How the rearrangement occurs? So you can see first this methyl group migrates toward this carbocationic center to form this primary center. This is transient species. This primary carbocation is a transient species in this case, because after that step this hydride can migrate over here to give you this tertiary center. So to generate this tertiary carbocation, the generation of this primary center is necessary. So that's why it is forming, and at the end you are getting this tertiary center, and on that any nucleophile can attack, and you will get the desired product. So this is how rearrangement occurs. And our next rearrangement reaction is a very popular and well-known rearrangement reaction, which is called Wagner-Meruin rearrangement. So in this case, you can see by this rearrangement, this OH group leaves from the molecule, and this methyl groups comes from here to here, and you are generating a double bond over here. So how the reaction occurs? So in the first step, this oxygen of this OH group, it gets protonated, and it leaves as water molecule, leaving behind this carbocationic center. And now this methyl group migrates toward this carbocationic center to give you this tertiary carbocation, and from this tertiary carbocation the proton gets eliminated to give you this double bond. This is the Wagner-Meruin rearranged product. Okay, so this is how the rearrangement occurs. And if you look at this, there is the empty p orbital, and this this CC sigma bond, it is exactly parallel to this p orbital, so migration is very easy in this case. So this is how Wagner-Meruin rearrangement takes place. So these are the reactions of carbocation. So we discussed all the reactions, stability, and how you can generate carbocations. So this is all about this lecture. In the next lecture, we will discuss about other intermediates, that is the carb anion. Till then, have a good day.